Let's take a look at another example. So this one just says prove that this equation is an identity for all permissible values of x. So it's not asking for the MPVs. While they do exist, we're not asked to find that. Now, if I look at my left side versus right side, the left side really is fairly simplified already. We've just got sine x. The right side, though, has a secant x in there, another secant x. So maybe that's the side we can start simplifying. Now, it might be really tempting to turn this into the secant into 1 over cosine, but that might not be the best step to start. If we go back to grade 10, and we think of the GCF or factoring, well, there's actually a secant x in both terms. So I can factor that secant x out, and we get 1 minus secant x. The denominator at this point is going to stay the same, so we have cosine x. It doesn't look any simpler, and now I'm going to do something that maybe looks weird, but it's only for the sake of showing you. I'm actually going to rewrite this out as secant x times 1 minus sine x over cos x. Now we haven't changed anything because if you remember, sine x can be written over 1. So if we actually go sine x times 1 minus sine x, well, that's the numerator. And then 1 times cosine x is the denominator. So nothing's changed. However, what this does allow me to do is I can easily just reciprocate sine x into 1 over cosine x. And I'll leave the second term alone, or second factor in this case. And now I'm going to do some multiplication. Well, 1 times 1 minus sine x is just 1 minus sine x. And then cos sine x times cosine x is cosine x squared. Now we're getting really close to what we're looking for. I need to get, if we go back to the right side, I see that there's a 1 in the numerator. So that means somehow I'm going to have to cancel out this 1 minus sine x. So looking at my formula sheet for identities, I can find that sine x squared plus cosine x squared is equal to 1. So if I rearrange that and isolate cosine x, well, then I'm left with 1 minus sine x squared. So I'm going to do that substitution just for the denominator. So we have 1 minus sine x, and then cos x squared is 1 minus sine x squared. Now it might be really tempting to start canceling because you see the 1 minus sine x, but the denominator has a squared on the sign. But what that actually is, that's a difference of squares. So again, if you remember grade 10, both 1 is a perfect square and sine x squared is a perfect square. So therefore, I can write it as 1 minus sine x times 1 plus sine x. Now it might be a little more obvious what we're going to do here. 1 minus sine x divided by 1 minus sine x is, well, 1. So then we're left with, well, 1 is our numerator, and then all we're left with is 1 plus sine x. And we got to make sure we actually finish this question. So therefore, left side equals right side. And yes, we've proven this now. Okay, right on. Let's go to the next question. Example 3. So again, prove this is true for any value of x, or permissible value of x. So if I look at the right side, there's not much I can do with that one. It's already very simplified. The left side has a double angle identity. It also has a sine squared. There's lots I could do here. It might be tempting to change both of these at once with an identity, but let's just hold on a little bit and think a little bit ahead. If I look at cosine, my double angle identities, you should actually find one that has a sine squared in it. And it actually happens to have a 1 minus 2 sine x squared. And then the rest just stays the same. Well, that makes this question really fast. Already, I have two terms that are actually the same or opposites. So they're going to cancel each other out. And all I'm going to be left with is 1 equals 1 already. Well, therefore, left side equals right side. And therefore, we've proven it. Okay, that was nice. That was a fast one. Okay, increasing the difficulty level a little bit. or maybe more than a little, we have again, prove that this is true for all permissible values. So I look at the right side, I see that's a double angle identity. Okay, we can deal with that if we wanted to. The left side is way worse though. We've got to this power of 4, power of 4. Well, there is no identities for that. So let's start simplifying this. Power of 4, well, that's a perfect square then. And so is sine to the power of 4 as well. So, and we have a subtraction. So what that means is this is a difference of squares. So then I know that cos x squared minus sine x squared, all multiplied by cos x squared, plus, because remember it's a difference, of sine x squared. I should write that, hey, I'm only dealing with the left side here. Don't care too much about the right side. This looks worse. Almost. Until you look at your identity sheet, and at this point, hopefully you know cos x squared plus sine x squared, hey, that's equal to 1. Oh, that makes this way better. So now actually we're just equal to cos x squared minus sine x squared. Well, you might be asking yourself, well, what do I do with that? Well, go look in your formula sheet. You'll actually find that this is a double angle identity, and this is equal to cos 2x, which is actually what we were looking to get. So therefore, the left side is equal to the right side, and we have proven this. So it's been proven. All right, final question of the video. Around the same difficulty level in this. So the right side, again, is a double angle identity. Probably not going to be my starting place because the left side looks way worse. We have some kind of term all squared. So that's going to make life a lot harder. That's probably where I would start. And I'm going to start by expanding this. Now this is a perfect square. It's possible that you already know how to do this without the step I'm about to show. But I'm going to show the full foil flowing out of this. So sine x plus cos x times sine x plus cos x. So it is a perfect square. Don't forget about your minus 1 though. That's going to become really important in a second. So actually doing FOIL, sine x times sine x is sine x squared. And then sine x times cos x is sine x just times cos x. And then dealing with our other term, so cos x times sine x. I'm going to write it in the same order. It's just still sine x times cos x. So yeah, that's right. The middle terms should be the same. It's a perfect square. Cos x times cos x is cos x squared. Do not forget about your minus 1. Now again, there's a maybe not as obvious step here. If I look, I have a cos x squared and I have a sine x squared. Well, I know if those two things are added together, that that's going to equal 1. So I'm going to write those as one term right now. Again, I'm making very obvious what I'm doing to somebody who's looking at this. I'm not just making this 1 right away. I'm going to combine these like terms that are in the middle. There's 2 of them that are the same. So I'm going to write 2 sine x cos x. And then I still have that minus 1 hanging out here. Now, as I already said, sine x squared plus cos x squared, well, that's equal to 1. This minus 1, I'm going to put right next to this other one, and then I'll still just rewrite 2 sine x cos x. And now I have 1 minus 1, well, that's 0, so I'm just left with 2 sine x cos x. At this point, this is a double identity, so this is sine 2x. Now, hopefully, we have matched our right side. Oh, yeah, that's what we were looking for. Perfect. So again, making sure we actually answer the question. Therefore, left side equals right side. And we have proven this.